Again, recording this computer. All right, now I'm recording.
Yeah, now perfect.
Cool.
Yeah.
So to summarize, anyways, maybe somebody new joined. Okay, I'll repeat for the recording. So I'm going to be presenting here the core part of the paper that we have on archive on analytic manifold learning, and that's joint work with my hosts at Microsoft Research Cambridge that I visited last year, Sam Devlin and Katja Hoffman, and Max Majdansky, who is a mathematician who contributed a lot of the mathematical aspects of to this, and my advisor at KTH, Dan Sakrajic. So first, I would like to turn your attention to this general setup that we usually consider in machine learning when we are thinking of embedding some high dimensional space, think of these as pixels, into some lower dimensional space. We usually take something that I would call a mapping view. And what is this? So we take some function f of our high dimensional input, these here are pixels, and we produce some low dimensional embedding. And that may have some nice structure. But how do we do this? So basically the algorithms, it depends on the algorithm that you're using to produce this mapping. This algorithm might have some desiderata. For example, maybe you have some natural metric on this original high dimensional space. Maybe you want to preserve something about this metric. Like for example, if you change only a little bit the, let's say, representation in a high dimensional space, you don't want to be suddenly completely teleporting to some different place in a lower dimensional space. So this is one aspect that you might be interested in. And there are other things like, for example, if you're doing something like PCA, then it's a different criteria like maximizing the variance while also getting your target kind of embedding correctly. So the view that this offers is that we are learning the latent submanifold as represented implicitly by this mapping from a high dimensional to a low dimensional space. And when you think of autoencoding, for example, this is kind of the most unsupervised automatic, or one of the most unsupervised automatic ways of doing it, where we're not guided by anything other than, let's say, reconstructing this back into the original space, and the structure of this latent space kind of emerges automatically. So here, both the encoding and the decoding maps are involved, but it's again, it involves some sort of implicit representation of this lower dimensional manifold via us learning this mapping. Okay, so I'm considering here, so in this work, transfer learning setting. So for robotics, for sim-to-real, we would have some images, and then here there are still simulations, but for the purpose of this talk, we pretend they're real images. Okay, they have real images of meshes of YCB objects and their visualizations. So this is our target domain. If we're like demonstrating proof of concept on sim-to-sim, these are going to be just like sophisticated images or renderings, but really we're going to be doing sim-to-real. Ultimately we would want to do sim-to-real, right? So when we do this for the purpose of the transfer learning, we will again on the target domain have to learn this mapping from the high dimensional to low dimensional space. Except now the question is, how do we incorporate this information that we already have from our source domain? So in this mapping view, how would we do it? Well, what can we usually see in various works? We would take this F and we would fine tune it. So what's the problem with that? One problem is if you're using neural networks, and if these are fairly sophisticated neural nets, you would have something like catastrophic forgetting pretty quickly. You can demonstrate this in various ways. You can also have bad local optima because you will start with a representation that is, and with this mapping that is optimal for these images, but it might not be optimal at all for these images. So rewiring it might get stuck in a local optimal, and you would get bad kind of fuzzy, bad results. And the other thing that would also have to happen is, in order not to lose this structure that you've learned here, you might have to set your learning rate pretty slow. So this means that this high dimensional to low dimensional mapping would be adapting pretty slowly. And that is not what you might want, because you actually might want to adapt from few samples or quickly. So that's the problem with the mapping view, but I know that there is no issue with the mapping view in general. This is just, I'm saying, I'm focusing on the case where I'm using this for the transfer learning problem. And for me, of most interest is the sim-to-real problem, but in general, the transfer learning problem. So what can we do alternatively? Alternatively, we can specify this latent submanifold as a set of equations, or in this work, we'll call them relations, same thing, that have to hold on the points of this on this submanifold. So overall, the submanifold is represented as a null space of a set of functions. And that is basically the key kind of difference in the view, in the approach that this work takes. And here, let's just take a look at a very simple example. So we are representing an ellipse, so like this thing outlined here in red, dashed dotted line, as an intersection of a hyperboloid and a plane. So there's only so much that I can illustrate in 3D, so maybe it's not so interesting, but this is here is an intersection of two relations, G1 and G2. So overall, this is what, the kind of the overall goal of this work is to be able to describe these the latent submanifolds that we're working with by a set of relations. And the algorithm is how to do this when nobody tells us at the beginning kind of what this relation should be. So why do we want to use this relations view? So this view allows us to encode the latent manifold directly. What does this mean? So we might have some a priori knowledge, or we might have some data that is coming from simulation that doesn't require us to render anything in images or in point clouds, but we have the low dimensional state that is already kind of encoding the information that we're interested in. So for example, two-linked arm, we know the configuration space of this is a torus. So this is like one very obvious kind of low dimensional structure that is already there. There's no need to kind of like rediscover it every time that we're working with, images or point clouds of this thing. Same thing here, for example, if we have some sort of a dynamical system that is encoded either in a set of equations or in a black box simulator, what we can do is we can basically sample observations from that as we are maybe just observing the system if it's passive dynamics, or interacting most likely with the system and using the actions as well. And I will explain later what this image means. And we basically understand what the data manifold, what is the data manifold that corresponds to this system. And then we can directly use this later on to transfer the knowledge about the structure of this manifold when we are learning on our target domain. So that's overall the setup. Now, the key question here is, emphatically, I do not want in this work to rely on domain knowledge about what these structures might be. In robotics, we used to do this a lot. I work on learning for robotics. So of course, I would want to learn all of these things automatically. And most of the time, my work is mostly in sim-to-real with black box simulators. So I do not want to have any deep insight into what the simulator is doing. It's a black box thing that gives to me maybe some low dimensional observations and also high dimensional observations, and that's it. Okay. So previously, what have people done with this? There have been some steps in trying to basically say, I have some previous knowledge about what the latent space should look like. Let me use this knowledge and impose the sort of, not constraints, but relations or this knowledge on the latent space when I will be learning later on the target domain. And one thing, so this is just to illustrate a very easy to understand conceptual idea. One thing that people have suggested is we will impose continuity on the latent space. So when we're learning already on the target domain, we say, okay, maybe we don't know anything about how the embedded the latent space should look like, but we know that consecutive states, they shouldn't be jumping all around. They should not be too far apart. And this continuity, it holds for many systems. Of course, we also know that it doesn't hold for some systems. Like, for example, if you have a contact-rich task, you can have high discontinuities, both in dynamics and of course then in your cost function. And so that would be problematic. And so here it would mean that from the previous state to next state, actually, depending on how high of a frequency you're sampling at, you might have big differences. So what this demonstrates overall is that you can come up with some heuristics that would kind of tell you which relations you should be imposing on your latent space, but it is not general, and you would have to come up with by hand kind of what holds for each particular new system that you are considering. So that's what we're proposing to do here. We're proposing to take a broader view and to learn a set of relations that are non-linearly independent that somehow help us describe this latent manifold. And the kind of key component of this work is that we want to define independence rigorously. And I will show you why we want to define it rigorously, because in the linear case, we're all familiar with the linear case, so there is no problem there. But in a non-linear case, it is actually non-trivial to say what this means. And the initial motivation also for why we want to learn kind of with independent relations is because we want to have a sequential algorithm, as in you learn one relation that maybe captures a lot of the aspects of the data, but it's rather simple. And then you learn further relations and kind of the intersection of all of them. This is what gives you an information about the whole latent data manifold altogether. Okay, so that's the setup. And now I will go through a little bit of math. So unless there are big objections or like key questions on the setup, there are no key questions on the setup, then I continue. Okay, so here we are focusing on a part of the overall problem that I described. And this problem is learn to capture the latent data manifold or submanifold by a set of relations. Okay, so we forget for now about the high dimensional space, and we consider the subsequences tau here that come from our dynamical system. Either it's, analytic equations or like some mess of, a black box simulator that emits for us state, next state, and so on. And usually we're interested in how the states and actions interact as well. So the subsequences here that I will be considering are like state, action, next action, and so on. All right, so the Rn here will be the ambient space of all possible latent subsequences. So that means that, the strings, they don't have to be coming from an actual dynamical system, right? But the taus here are going to be like the data manifold is going to be consisting of the sequences that we actually observe, that we actually can sample, that are feasible with the dynamics that we have. All right, so this M is going to be the submanifold of actual state sequences. And our goal would be to capture this with a set of relations. So how are we going to do this? So in linear algebra, if you recall, the dependency is a linear combination of vectors with constant coefficients. So if you can find a linear combination of vectors with constant coefficients that can express your new, let's say, vector, then it's not independent from the previous ones, right? So we're going to have a very similar reasoning here. So this comes from abstract algebra directly. And the notion, the generalization of independency to the nonlinear settings is called a syzygy. All right, and so here you can just read off kind of directly the same formulation. So we would have a collection of functions. So now we don't have coefficients, which are scalars. We have functional coefficients. So like functions are our coefficients. And a syzygy is the sum of these functions multiplying our relations. And if the sum is equal to 0, then we call this this kind of, we found a certain relation, right? Just like here, we would find a kind of a dependency here. If we can sum this up, multiplying by these functional null coefficients, and this, the result would be 0. So if there is no syzygy such that this, sum equals to 0 is such that we can find a set of coefficients, functional coefficients such that the sum would be equal to 0, then our relations are independent. So that's great. It's very comfortable. It's an established field, comes directly from another field, has a direct analogous to the linear case. However, the problem is that with this notion of independence, you can see very quickly, right, that these functions f, if they have the same, pretty much the same type as g, right, then you would deem everything dependent. Because you're going to say, okay, well, let my first coefficient be g1 multiplying g2, and then the second g2 multiplying g1. And well, this always holds. This is the equal 0 always holds. So everything is always dependent. And so this is a demonstration how in mathematics, frequently you need to work actually before you start doing any algorithmic work. You need to come up with a set of definitions that actually make sense. So here, this definition, while it's kind of valid and has a nice analogy to the linear case, it is, it just deems everything dependent, so it's not very useful. So we say, okay, what can we do? We can restrict the kind of flexibility of these syzygies. So we come up with a restricted syzygy as follows. The last coefficient, the one that is for our last relation gk, we're going to be setting to 1, just fixing it, and saying, okay, well, can we find the k-1 coefficients such that when we set, such that when we're putting them into the sum, and have the last coefficient as -1, we can have the relation that that this whole sum is 0. Not relation, but we see that this whole sum is 0. So this defines a restricted syzygy, and with that we define restricted independence. So restricted independence is, the same as we had before. If we cannot find a syzygy, so meaning the kind of relation between relations that would have, that would have the sum equal to 0, then these g1 through gk are independent. And now they're independent in this restricted sense. So this is a different definition. And now let's see if this helps us any, right? So, okay, somebody else is joining, right?
Can I ask a question?
Yes. ask a question.
So why did we have to move to nonlinear independence? Why wasn't linear dependence sufficient?
Because we want to learn G's that are arbitrary. Jumping ahead, we would want G's to be arbitrary analytic functions, and we will approximate these functions by our favorite tools, the neural networks, right? So if we wanted like some set of linear functions, right, then we could ask whether they're linearly dependent or independent. And this research, I mean, there is a lot of research that just maps to some space where you want to operate with linear functions and relations and so on, right? And then you're comfortable there. And all we're saying is that like we don't really want to map to that space. We want to have a set of relations which are quite flexible and not necessarily linear. So that's why we want to move there. Yeah.
But flexibility, I mean, if we think about Fourier decomposition, for example, that's also very flexible.
Yes, so the point is this. When you choose a way to do the mapping, like for example, you say, oh, I will pass to this new space, which is defined by my Fourier transform or some other transform that I like, right? You are already committing to how it is that you're going to be doing this, which space you're going to be operating in, right? When you're doing the linear thing, you're saying, okay, I will put a lot of work into finding the embedding that will make my stuff in the lower dimensional space linear, right? And so you would need to do a lot of work there. And what we're saying is like, well, let's take a look at an alternative. Don't do a lot of work. Instead, learn relations which would themselves be pretty complicated. So it's like you encode the complexity in its relations, right? And you can argue whether one approach is better towards the other. I would say that a lot of the like established techniques, like for example using Fourier transform and stuff like that, for the signals that that are really like for which these features work really well, great, you should be using that. And then sometimes they would be insufficient, and that's where you might want to look at something like what we're offering.
Got it. Thank you.
Okay, right. So that's what is happening here? Oh, right. That's the setting that we have. Right. So with this restricted independence, first we want to show, I mean, this is just a mathematical thing that we want to show, is that this process of adding new relations is finite. So like really we have found some way of encoding independence where we would keep on adding GKs, but at some point this process will terminate. And we can also define, I won't go too much into the detail here, but we can discuss this with people if they're interested. We can define a strong independence, notion of strong independence, with slightly kind of changing the definition of how this is done. And with the strong independence, what we can say is in the paper, the theorem is worked out to say that every time we add a new relation GK, we're actually adding new information, a certain amount of new information, in the sense that the dimension of our data manifold is dropping. So basically the relations, like we start with kind of like ambient space, and we cut out this ambient space by adding more and more relations, right? And we want this dimensionality to be dropping because we want to kind of find, in a sense, like the minimal, the lowest dimensional representation of the latent data manifold. So that's what we can have here, and this is like you can have the mathematical guarantee for that. So another thing that you can do with this framework is you can have an alternative definition with transversality. So what this gives us is that, okay, let me first state what this proposes to do. So we ensure that relations differ to first order, meaning that their gradients are orthogonal, or we push them to be as orthogonal as possible. So with that, this can be kind of linked to techniques and objects in differential geometry. And what this gives us is this gives us a way to basically make relations kind of quite different from each other, but perhaps having also simpler shapes. So not linear, but I will show kind of examples later. Not linear, but simpler. And this is also kind of a faster algorithms with fewer moving parts, fewer components, no syzygists here. So that's an alternative thing that we also show how to use in this work. And with this, for once differentiable GKs, which will be in our case, since we're going to be approximating them with the neural nets, we again have a lemma that shows what happens to the dimension of the latent submanifold when we add a new relation that is transverse to the previous relations. Now, in the algorithm that I will show, things will be approximate. Everything so far has been exact. This is just abstract mathematical formulation. But because these things would be learned from data, right, we would approximate them with, first of all, having finite amount of data, and second of all, actually having a neural network with a certain restricted capacity, representational capacity. So they will be approximately transverse or approximately independent in the restricted sense. And then, the point is to demonstrate that this approximateness is enough. All right, so that's the overall setting. So these GKs, as I said, they will be learned in our case, with neural nets. We don't take any prior knowledge. So this should just give us the data, like, let's say, from the simulated states and actions. That's it. So there is no other prior knowledge that's needed here. So, right, so this is here I'm rolling out, I'm getting the data from the reinforcement learning actors for other reasons, because I want this ultimately to apply to non-stationary data and be able to learn kind of from the streaming data. So that's why I do it. But for the purposes of just demonstrating what happens with the algorithm, okay, you get the data subsequences somehow, right? Then you train the first relation by basically saying, okay, well, the on-manifold data, so the one that comes from the actual observations from state actions from the dynamical system that we're running, or the simulator, the relation has to hold meaning like B0 on that data. So that's, and we have kind of an interesting regularization term here. Again, I can talk about it a little bit later. So basically to say that, and it has to kind of take off as you move away from the data submanifold. So that's how you would not learn a trivial relation of just everything being zero everywhere and you win, right? So that's the first kind of getting started with G1. And then if we're aiming for transversality, then we train each GK to be such that the gradient of this GK with respect to the input subsequences tau, so basically with respect to the data inputs, they are orthogonal to the gradients of the previous GK relations that we have learned, G1 through GK minus 1. Right, so that's how we proceed. And in the paper, we'll talk a little bit about how to express this, ensuring this transversality. What does this mean in terms of when we actually write down the loss function, and what would be like a good computationally like fast thing to do. And here we don't need any. This is all first order, and these things are going to be basically measuring angles between vectors. So there is not going to be anything computationally expensive here, which is nice. All right, and if we are using syzygies instead of transversality, you will see the relations then end up a bit more flexible. Then we have a little bit more work to do. So we set up an additional network here that is going to be the syzygy. And we're going to be trying to learn the syzygy that everywhere in space, so like not only on the data manifold, but like this tau off here means like off manifold data. When we input the off manifold data to the Gs, they produce some outputs. This of manifold data also goes into the syzygy. And then we are going to be trying to learn the relation over relations, which is the syzygy. That outputs 0. And if we succeed to learn this such that it outputs 0, that means that our next relation that we're currently learning, so here in this example is G2, is not independent from the G1. So it might seem a little bit puzzling at the beginning, but you don't have to parse any of this before. All this is doing is implementing directly the math that we have established. That's it. So there was this relation over relations, the syzygy, and it said, if you can find the fi times gi, all of them summed up such that they're 0, then they're dependent. So if you can find statement, this is a mathematical statement, but this is how we convert it to an algorithm. So we're training it, so like trying as hard as we can with just a neural network loss to say, okay, find me the functions, these f1 through fk minus 1, find me the functions that when used as functional coefficients to these relations that I have would produce, like the dot product of these things would produce a 0. And if I can find such functions, that means that these are not independent. Okay, so that's the setup. And then what do we do? Well, if you find such a relation, then we set up a way to use the loss such that we push the G2 away from the current solution which basically makes it like not the G2 that we have been learning that made it possible to have the syzygy, so relation over relation. So basically we freeze the syzygy and say, look, I found the relation between G1 and G2. Okay, so G1 is frozen. I'm already done learning it. Now push the G2 away with kind of the same loss, but now make it in the opposite direction. Push this G2 away from the current solution that it had. Okay, so
Sorry,
yeah.
One more question. How do you generate of manifold data?
Oh, that's very easy. So basically, you can take random data because when you think of like going in a higher dimension, the probability of hitting a point in a lower dimension on a particular manifold is effectively 0. So that's what you can do. You might say that, oh, you don't want a completely random stuff. You just want to thicken the manifold, and that would work as well. So this is a completely non-issue here. So as soon as you have some data, you can either thicken the manifold, because then you would have the networks that learn kind of what happens around the manifold, which might be more interesting to you than what happens in the random part of the space. But if you're working with something like fairly small and low dimensional, then you can also say, okay, just sample me random sequences, and that would work. Right. Okay. So then the colors here, we're just trying to illustrate that weights of this G2 are not fixed, and then the weights of this G1 are fixed. So this is our sequential way of producing, once we learn G1, we're done, and we'll continue to learn the next one, right? And what we do with the syzygy is we ensure that the next relation that we learn is independent from G1. And then when we're done ensuring this, then we add this, G1, G2, whatever, up to GK minus 1 that we've learned so far to our set of relations that have been trained, and we train the next GK. So that's basically how it proceeds. So the part here that, that our restricted syzygy definition and restricted independence is encoded in this thing. So at the last layer of the syzygy, we say, okay, we will interpret each output of the next to last layer of the syzygy as a functional coefficient, because that basically means we take some input, and the syzygy, being the neural net, is just an arbitrary function that produces some output based on this input, right? And then we dot product this with the outputs of our relations on off manifold data. And before you ask, the reason why this is the on off manifold data is because on manifold data, we have trained them to be 0 or close to 0, right? So just combining zeros wouldn't make much sense. So that's why this thing is taking the off manifold data. Okay, so that's basically the algorithm. And to visualize kind of how the results for this look like, so recall our example here with the intersection of the plane and hyperboloid. Here we add some noise, so it's not an ellipse, but it's like some sort of an ellipse with a noise. And if you use training with transversality, very easily you come up with two transverse relations. So this is a plane, and this is basically at an almost the right angle to it, a hollow cylinder, right? And the intersections, these are the 0 level sets of these relations. So, I'm just plotting, like this is all from data. So plotting where they become 0. And the intersection of these 0 level sets is exactly kind of like very, very close to the on manifold test data that we had. And if you insist on learning more relations with transversality, that's why I was saying you would end up with simpler shapes. Now this is enough, like 2 is enough here because we're in 3D. But if you insist on learning more, then you would get these cones that are also somehow kind of simpler shapes, and also trying to be as kind of transverse as possible. They're not at the right angles to each other, but they're at large angles to each other, well, at the point of intersection. And when you train with restricted syzygies, what you get is you get relations that have, first you get something like a bent plane, and then you get relations that kind of wiggle around and change a little bit. But overall, with 4 or 5 relations, they also capture this data manifold. And why would you want this? This seems like a non-minimal representation. But the reason why you might want that is because, for example, if these are policies, then maybe you don't want to have a policy that is vastly different from your previous policy. Or if you want something like a small adjustment to your current kind of conception of what the data manifold is, like, for example, you're doing transfer to a very similar domain, then this is something that you'd find desirable. So that's overall the setup. I will, why is this going in a different way? There are a few more. Sorry, the recording thing moved to the top, and I don't know how to, okay, I moved it to the bottom. Right. We show results on playing with sliding block on incline, adding various nonlinear effects to it, like drag, for example, and kind of showing that the intersection of the learned relations for us can basically encode the low dimensional data manifold. Here we're not in 3D anymore, so I can't visualize kind of like 3D shapes for you. So these are phase space plots, meaning that we plot position and velocity, and the arrows indicate position and velocity at the next time step. So this is passive dynamics. This is just block sliding on the incline, and that's what we get. And the fun thing is that we can actually demonstrate generalization. So if we train on this range that is in the gray box here, when we compose these relations, we get kind of on the wider range, something that resembles very much the on manifold test data for even the regions that we haven't directly seen. So that's nice when you kind of this basically shows kind of like ability to generalize a bit. And how this will overall be is applied to transfer. I won't go too much into this detail, but basically if you're using, for example, something like a VIE, what you can do is you can train on your source domain. This can be either just taking, directly the simulation states. And then on the target domain, so this I'm here doing sim to sim for now, but you can imagine like if you wanted this to be real images of your domain, if you're learning, if you're training a VIE on a target domain, what you can do is you can impose the latent relations that you learn to structure your latent space. So how would you do this? You would change the standard evidence lower bound. So you use the standard evidence lower bound like you usually do in VIEs. And then you would add an additional loss, which would say that, oh, by the way, the latent relations have to be kind of like the output from them has to be 0. So this would kind of impose the structure that you have learned and kind of bind the latent space to be similar in structure to the latent space on the simulation whose properties you are trying to capture. So that's overall how this is applied here. Again, I can kind of go through the details if anybody needs questions, but I think I am over my 30 minutes. So what I'll say is that this helps us predict better the alignment between the position of the object in this case. So this is what we can measure here in the sliding block example. This also, we can also show that we end up with an encoder map which has lower distortion. So that better preserves the geometry of the low dimensional manifold. That's nice. And this is just using some distortion metrics that are similar to what's been used in literature before. And there are a lot of kind of future directions. I won't go through this too much. There are a lot of future directions where this compositional nature of this allows us to say, okay, for the lifelong learning, we could actually go and learn kind of new relations and then come back to using the old relations if we want. We can also adjust the weights of these relations and kind of transfer the weights as well. So that's nice. And ultimately, of course, what I would want to do, you don't have to read this. This is just showing that what you can do is you can store, when you're doing the lifelong learning, you can store the lower dimensional relations. And if you can't afford to store the high dimensional mappings from images or from point clouds to your low dimensional state, that you can discard those and relearn those, but still be able to keep the lower dimensional structure. And ultimately, of course, what I want to do with this is I want to put this on a real robot, because that's a bunch of my previous work where I usually started was thinking of how I'd set up the hardware experiment. And because this started in MSR Cambridge kind of collaboration framework, they don't have robots. So they think about, games RL and variational inference. So I started with that, but now ultimately what I want to do is I want to do not sim to sim, but sim to real with this. All right. So that's the summary.
I guess we have time for some questions. Thank you for the amazing talk.
Questions? Otherwise, we'll just be looking at robots.
If nobody has any questions, I have questions.
Yes.
Okay, cool. So I like this method a lot. So it reminds me of function space generalization of Gram-Schmidt, and it's super cool.
That's yeah, that's an interesting comment. Mm-hmm.
So there are methods in. So have you looked at gradient-based regression, where they also try to learn, the next function that's going to help you reduce the loss, but the functions that you learn in a sequence are not exactly are not necessarily, independent?
So here, the reason why, okay, so let me see. Because our functions here, our relations here are very flexible, the notion of independence is also flexible. So what this really boils down to is, because if you think back to the linear case, there is sort of only one natural way to define what independence is usually. So there's very little room in kind of saying, no, I will have a different definition of independence. And in the non-linear case, like I was showing here, like there are just a bunch of different ways to say what it means to be independent. So what it all comes down to is having some statements about, okay, how I define independence, and then saying something about, okay, and how does this help me to capture new data? So there are a bunch of ways of doing it. Like, for example, you can say, I want to have the next piece of information, relation, or whatever it is, such that I capture more information in the sense of something like mutual information or something else, right? So it might be probabilistic in nature, and then you're not looking at something independent, but you're looking at something that fundamentally contributes new information. So I think the whole point here, because everything is so flexible, the whole point here is not really dependent or independent. It's more like, can this notion of independence help me set up the kind of sequential learning algorithm such that it can say, oh, and by the way, each new relation contributes this sort of aspect, right? So either I can say drops dimension, or I can say eventually my sequence, each new one doesn't drop dimension by something concrete, but when I am done, when I've terminated, I have learned the data manifold and so on. So I think that's the point. So you can have other algorithms, and then it's just a matter of whether they work better on your data and computationally whether they're better for you. But ultimately here, what I want to emphasize is like this notion of independence is not very rigid in a sense that kind of you are more in control of defining what you say is independent. And then the whole point of saying independent is says that I can show that new stuff I learn brings me something, either by dropping dimension or by capturing more of the latent data manifolds in some other way. Yeah. So what we looked at, for example, like after we were, I won't go into how this came around because this came around basically from, let me see, actually, maybe, yeah, it's just right here. I was looking at the survey, and in the survey, they have a whole section of what you heuristically postulate about relations of the state. So like slowness principle, continuity principle, and there are other things to say that mutual information between the pieces of consecutive state, different consecutive states. So there's like a bunch of work like that thinks up in your head, like what is it, the relation effectively, right, that I want, and kind of adds it as another heuristic, and basically a combination of those heuristics is added to the loss. So that's how this whole thing started. And so when we looked actually after we have, we were done with formulating this and doing experiments, we looked at, okay, what prior work is closest to this? And what actually one of the closest things are the things where these relations are polynomials. And there's a bunch of work where you learn kind of in some sense, like sequentially the polynomials or altogether in batch the polynomials that capture this whole thing. But of course, for us, it's not as interesting because, and they have very nice mathematical results, and it's much easier, as you can imagine, to work with that stuff. But they don't have the flexibility of this being any analytic function and being approximated by a neural net. So that is the closest. And we actually have like a big section in the appendix, which lists all the kind of work that is kind of by inspiration. It seems to be kind of quite similar, but they have different math involved and kind of the different mathematical kind of constraints because you are working with polynomial functions.
Gotcha. Thanks.
I have a question about the training process with reinforcement learning. So is the manifold learning or the latent space learning kind of disjoint, or does it occur in an interleave manner? So after you execute rollouts, do you learn a new manifold based on that rollout and then again loop over, or is it separate?
Right. So you will notice in the first part of the paper, actually, this was about looking at limitations of the current methods when they learn on non-stationary data. So when I go back to this like little line here, I think we're talking about this, right? So this is training on the source domain. So in a sense, you can say, oh, well, I have a lot of data here, so it doesn't matter. And the reason why I learned from RL here is because I wanted to make sure this algorithm can handle non-stationary data. So that's it. So it doesn't do anything weird when I sample these subsequences and they're not on a nicely kind of like outlined data set whose, learning I can fully control by decaying my learning rate in any, nice schedule that I can come up with. So that's why this thing is rolled out from the actors. And on the target domain, you're transferring information. So you're not obliged in this like initial setting, you're not obliged to adjusting your relations anymore. But again, the reason why I did this thing from RL is because in the future, right, what I want to do, like what I alluded to here, in the future, what I want to do is I want to learn a bunch of relations and then move to the next domain that is not my previous domain. And I want to be able to evolve the latent space relations as well. So this I haven't done yet in the sense that I have kind of built the algorithm to accommodate this sort of scenario, but I haven't kind of like actually wired this thing to see what weights are being learned and can I like come up with new relations quickly and forget the relations quickly. But the reason why this algorithm is set in a sequential manner is precisely because I want to keep the relations that, transfer the relations from the kind of my immediately previous domain that I have experienced before. And instead of having to batch relearn everything, I just say, okay, but what about on this current data? Can I learn a new relation that somehow captures the data manifold better because it's now a new data manifold? So yeah. But this is why it says current and future work, because even though this is specifically designed with this kind of lifelong learning scenario in mind, that's the, that is not, the results for that is not in the paper. So that's what we're working on now.
Okay, thank you. More questions?
Yes.
So what about viewpoint variations?
Viewpoint variations, can you say more?
Yeah, so do you think if I look at, so you showed a sim-to-sim scenario where things were rolling down a plane, tilted plane. So if I were to look at that from a different viewpoint, would the relations, the learned relations still be useful?
Yes, relations would be, because relations are not learned on RGB data. So here, that's why I draw here like this little thing. So they are learned from a black box simulator that has a simple shapes, and my tau sequences, state, action, next state, state, action, next state, that's the state like, oh, position orientation of my object, because I have access to this, right? So in the sim-to-real setting, like that's not the case in general. The algorithm is very general, so it doesn't have to have a simulator inside of it. But in a sim-to-real setting, in sim, your kind of your lower dimensional data manifold comes from your simulation. So that's what you get for free. You don't have to worry about the viewpoint. Here, you would have to worry about whether you have like ability to learn from different viewpoints on the target domain. And that just comes down, so this is now separate from AMOLED, it comes down to how powerful your algorithm is that proceeds to learn the high to low dimensional embedding on the target domain. So the hope is that you are transferring enough of the low D kind of structure, but you still need to learn this mapping if you have only high dimensional observations on the target domain, right? So that's, and that's exactly like, I would give the kind of, the other result that I found while working on this is that, for example, a lot of the VIEs are not strong enough to do this. They suffocate on the decoding step. So they inherently have this limitation of, because I only have the pixel loss to guide me, and if I have many, that's exactly where these things get stuck. If I have many different objects, like this is not even the worst scenario. The worst scenario is the one with many different objects, all kind of moving and all basically being free from the robot, because they all have kind of 6 degrees of freedom each object, right? And you have a bunch of freedom there and a bunch of angles that you will see them from. So that is a limitation, but now this is not a part of AML, but what algorithm you're using for doing this encoder-decoder mapping. And that's why for the future work, I'm actually moving much more towards not having the decoder-based methods. So something that still learns that you need to learn the high to low dimensional embedding, that's fine, but something that learns it other based on auxiliary tasks, like, guided by the, okay, I need to complete a bunch of tasks, and or something that basically has a signal that guides it directly, instead of saying, yeah, reconstruct me pixels, because pixels is like too weak of the of the loss. So that's so the issue here is not with the low dimensional part of it, and the issue here is, can you find an algorithm that can do this high to low dimensional embedding on the target domain that is sufficient.
Had a quick question that's like more implementation detail, I guess. For the learning of the Fs, you say you freeze the previous F. Is that not too restrictive? Because
so here the whole algorithm, if you're familiar with maybe Frank Wolf algorithm, maybe, or any maybe boosting things, something like this, right? So if you're familiar with those, the kind of fundamental nature of this algorithm is I have a first component that I learn. It doesn't have to be independent. There are other criteria, right? And then I add this to my current set, and then I learn the next one that is somehow good, and the next one, and so on. So this is one of those, like, this is actually inspired, like I started this work by being inspired by Frank Wolf and did a few kind of versions of how this could be incorporated directly. But this doesn't directly incorporate Frank Wolf, but this is exactly the same idea. The G1 that I learn, I want to make sure that it's good. So this is what is done by this like initial loss. The G2 that I learn, I want to make sure that it's good in the sense that it also holds, like output 0 on manifold data, but it also is already independent. So when I'm done learning G2, that's why this thing here is saying, I will only stop learning G2 when I am happy that I cannot find the relation between these two, G1 and G2. And that's why I can freeze it, because then I know that the G2 does contribute something new in comparison to G1. And when I learn my G3 and so on, I know that the next one, I am looking for a relation that specifically contributes something new to the set of relations that I already have. So that's why I am able to freeze them, because it's not in an ad hoc way that I decide to freeze them and so on. The algorithm is structured in a sequential manner in the first place.
Right, but you don't freeze F2, I guess.
No, the F I only freeze when, so let's say here I found a relation. So like F here, the syzygy just says, yay, these two are related. So then I freeze it and say, okay, now push away G from the current solution, because while the current solution is not very interesting, these two are dependent. So then I freeze the F, and then you keep going. Yeah.
Any other questions? People are shy.
Yeah.
Is there any special considerations you have to make if the dynamics are stochastic?
No, because here they are stochastic. We start right away with the noisy things. Like here, I don't have any dynamics, but it's just testing that this is robust to noise. So no. And here, let me go back. These rollouts from RL actors, they are doing PPO, so a stochastic policy. So you don't need to say anything. It's curious, many people these days, they gravitate towards formulating things in a probabilistic manner. So here, of course, there's something probabilistic when you do like the imposing this onto the, adding this as a part of elbow, right? So that formulation, if you're doing the VIE on the target domain, then that formulation kind of is a part of generative model. There's some probability stuff here. But this thing itself, it like, works with things that have stochasticity in them, but it itself doesn't formulate anything in terms of probability distributions. And on one hand, like I see probably there is pretty much a way to semi-reformulate this in such a way that it would be probabilistic. But I am fascinated by by algorithms that there are a bunch of like older and more classical algorithms that don't have any probability in them, and they work beautifully. So that I think that part of my motivation is like exploring things that don't necessarily say I have two distributions, let me minimize KL, you know, because that's kind of what we do all the time. So, you know, something different.
Because in a way, it seems like in this formulation, any possible transition should be assigned 0 by the relation.
The transition that comes from your data manifold, yes. So if your system is, that's why I was saying under any control policy, like if your system is able to produce this transition, then you say, oh yeah, that's the part of the patterns that I can see. So you take it as on manifold data, exactly, yeah.
One more speculative question.
Yeah.
So if you wanted to do sim-to-real transfer or sim-to-sim transfer with different morphologies, so say I drop a leg from my robot.
Yeah.
What happens to the transfer then?
That is what is currently not in a future work. Very good observation. Yeah, so here, and that in part, I've done a lot of stuff on sim-to-real. So basically like all of my PhD work ended up being sim-to-real. And the way that we usually do sim-to-real is we construct a simulation that morphologically, like we are able frequently to construct a simulation that morphologically has the same structure. What we are usually unable to construct is that the dynamics, like how the system evolves, diverges pretty quickly between the simulation and reality. And so in that sense, like since I didn't face this as a main limitation, like, yeah, I can always set up a robot that in terms of its morphology matches exactly the target robot that I have in the real world. Since I didn't face this limitation, I did not set up this algorithm to just natively say, oh, by the way, what if your morphology changes? So this really, you can relearn, you can kind of have the source domain, which matches your target more and relearn it, or you can say, well, the thing is that here these relations hold, but you're imposing these relations in a soft way. So that's kind of one way that I can say that this this accommodates it, because this here is just a part of an elbow loss. So the one way that it accommodates not only just differences in morphology, but just like a big difference in general between the source domain and target domain is it says, I am not going to impose any rigid constraints on what your latent space should be that you end up with on the target domain. And that's in part where it accommodates this, but it doesn't accommodate it in an explicit way. Like, let me take out the leg and then, you know, I can actually take out one GK and there you go, right? This doesn't do it explicitly. So it does it implicitly in the sense that, so I very much like I don't work with constraints because then I need to know a lot about my system in order to say what the constraints are. And usually the settings that I want to work with are like uncertain. I don't know, like the reason why I'm doing sim-to-real is because I almost have no clue what would happen. And my simulation gives me some signal, but really not a very strong signal. And so in the setting, that's why these relations are imposed in the soft way. So like you would hope that they bring in some structure and help you learn faster, but they're not restricting what the latent space would look like. Yeah, but it doesn't do so in an explicit way for specifically morphology changes.
So if there are no more questions, let's thank Rika once again for a wonderful talk.
That was fun. You had good questions. It's great. Yeah. Thank you.